All right, folks, we're going to look at one theorem from section 3.10, which is the mean value theorem. So I've copied the theorem there, and it states that if f is continuous on a closed interval, which is important to note that this is a closed interval, and it needs to be differentiable on that same interval, but notice that's an open interval, so we don't necessarily care about the differentiable at the end points of this interval. We're just looking over the interval. So if those two conditions are met, that it's continuous and differentiable on an interval, then there's some number inside that interval, right? C is in between A and B, such that this holds true. Now, right now, that kind of just looks like a bunch of jargon, right? The derivative at point C is equal to some stuff, but it's important to kind of like put it in words for a second here. So this is the derivative of a point. Which we called our instantaneous rate of change. But if we look at the right side, what we can see there is that's just our slope formula, right? It's just the change, the average change over an interval. So I'm going to label that as average change. Right? Where did you end up compared to where did you start over the distance in between them? And the average change, we know that is just kind of, we kind of think of that as like a line or a slope. But what we're saying here is that at some point, the instantaneous change will equal the average change over that interval. And when we think about that, it's way better to look at a graph of that. But again, what we're saying here in symbols is that f prime of c, our instantaneous change at some point will be exactly the same as the average change over that interval. So somewhere in the interval, the change will be exactly the same as the average change over the interval. Let's go look at some graphs for that. So here I have just a basic parabola. It is coming from x squared. I'm just limiting the domain so we can look at it better. So here's our curve. This is our function f. So what I'm going to do is I'm just going to label 2 points, a and b. So what we can see over a and b is that our function is continuous. It's a smooth curve, and it is differentiable on that same interval. There's no points that we could not find the derivative. So what we're saying is if we look at the average rate of change, remember the average rate of change is just where did we start, where did we finish, and how long did it take us to get there. So in other words, that average change, just our line, is just a slope, and it's a secant line, right? So I'm going to put in the average change between A and B. So over 0.2 to 0.6, we increased that much, which is now being visualized by that secant line in dotted blue. So what we're saying is that secant line represents the average change. So what we can find then is there's got to be some point C on this curve. So here's point C, and we know point C is somewhere in between A and B. So there's some point in here where the derivative at that point is exactly the same as the derivative, or excuse me, the slope of the dotted blue line. So I'm going to go ahead and put in the tangent line. We can see like right here, this is a pretty good estimate. The tangent line at point C, which is in dotted red, looks to be parallel to the secant line, or in other words, the average change. So I'm going to take a picture of this. I'm going to put it back to our notes, and so we can just label a few things so we can see where this theorem is truly coming from. So going back to we can draw on this, I'm just going to dump that into our notes here. Sorry, we're not looking at Rolle's theorem. So let's add that picture. And again, we're going to put this into the same words and the same symbols. So I'm going to put it right on this page here so we can compare. So let's add that picture. We're just going to look at the graph of this. That's all we really need. So what we can see is that we had some interval, right? So our average change, kind of mixing up my colors here, but our average change, which was here, That's denoted in blue. The average change of the interval a over b is that dotted line. Now there was some point on that interval, so we can see C is between A and B. So it's on that interval. And we can see is that the instantaneous change, the derivative at that point, which is a dotted red line, is the exact same value as the blue line. So if I just put a number to it just for the sake of it, let's say that the slope of this dotted line is just about 1, right, from here to there, almost 1. So we can see that the slope of the red line would just be the same thing. So we found some point in that interval, A and B, where the instantaneous change was exactly the same as the average change. Now it's important to kind of look is that this theorem doesn't tell us where C is. It just tells us that it exists. So again, if I start moving C around, this one is not the same. It's the same about right there. Here it's not the same, here it's not the same. It doesn't tell me how to find it, nor how many exist. It says there's guaranteed to be one of them. Let's just look at another function so we can kind of see the same thing. So I'm going to turn off the original function 1. We're just going to go to a new function. I'm going to kind of get a better picture of it. This is part of a sine curve, just to limit our scope here. So what we're saying is if we pick 2 points on this graph, let's just call them A and B, what we can find then is let's look at the average change over that interval. So it started negative, over some x values it turns positive. So the average change is that blue line. Again, we can see the average change in y, and we can look at the average change in x. So that line is representing the average change. So what that means is there's got to be some point C. I'm just going to go ahead and turn that point on right now. There's some point C, which is inside that interval, and I can change the color for us. Let's make that red just so we can differentiate. So there's some point C on that interval, anywhere in there. I'm not quite sure where it's going to be, but if I look at the derivative of that point, which I'm going to now put in red, or sorry, we'll make that dotted red instead of dotted blue. The derivative at that point, there's somewhere in this interval where those slopes, in other words, those rates of change are exactly the same. So like right there, I can see that the derivative at point C is equal to the average rate of change over the interval A to B. Now, it just tells us it exists. So there's one there. I think there's actually another one. If I come down here, it looks also like that has pretty much the same rate of change. So again, the limitation of the mean value theorem is that it tells us it exists. It doesn't tell us where it is. It doesn't necessarily tell us how many there are, but it gives us the proof, or gives us the, I guess, the reason to show that it will be there. So it gives us the reason to go look for it. So just 2 examples there. So the mean value theorem, again, putting it as words, somewhere over a closed interval where our function is differentiable, the average rate of change will exactly equal the instantaneous rate of change at some point. Now, there's a special part of this theorem, this mean value theorem. There's a special condition of that. Now, in our notes, that's called Rolle's theorem. So Rolle's theorem is just a special application of the mean value theorem, in my opinion. So what they're saying is F satisfies the conditions of the mean value theorem. And it's good to know what those conditions are, right? So we can always make sure to apply it appropriately. But the mean value theorem says it's continuous on a closed interval. It's differentiable on that open interval. All right, so we've met the conditions there. There's those 2 conditions. And then I guess the last condition of that would prove that there's some C in there. But those are the 2 things we need to use the mean value theorem. That proves the existence of some number C. But this is a special case. What if the average rate of change was nothing? Right, so they're saying here, what if the endpoints where you started and where you finished were exactly the same? Well, what would that mean? Well, to me, before we even look at a graph, if I start here, well, I'm going to actually put a little graph first. If I have a coordinate plane and I start at that x and I travel this, I go up there, maybe I come down here, I go over here, blah, blah, blah. But I end up the exact same place. So what they're saying is the average change here was nothing. But what does that mean? Well, it doesn't tell me too much about my path, right? I could have gone this way, I could have gone this way. I could have taken any path and say, well, I haven't changed my y value from start to finish. I could have gone this path, right? That one works too. Maybe I just literally just went from there to there, from this x straight over to that x. So if I start and finish at the same y value, it doesn't tell me the path that's in between there, but it does tell me one important thing about that path. It tells me somewhere in that path, my derivative, or in other words, my rate of change was 0. And this is where I start to connect the rate of change of 0 as a turning point. Right? If we look at just a basic graph, I'm going to put another one in, and then we'll look at a real graph here. If I have some y value, and again, I start right here. Now, I have to end at the same y value. So in other words, my change in y was nothing. Or in other words, if this was a and this was b, the change between the two was nothing. Well, again, it doesn't tell me where I went, but maybe I was going here. But if I'm going to get back to b, that means I got to turn around. So I'd have to turn around right there. If I took a different path, like maybe I went all the way down here, but if I'm going to get back to that y value, I have to turn around and come back up. Because again, this function's continuous. So there's no way I'm just jumping from here to there. So the idea is if I start somewhere and end at the same place, I must have turned around somewhere. And that turning around point would mean when our derivative was nothing, right? Rather than increasing my y values, I had to stop, turn around, and then start to decrease. So somewhere my change was nothing. I wasn't increasing, I wasn't decreasing. I'm simply turning around. Same thing over here. Here, I'm decreasing in my function. But at this point right here, I'm not doing anything. I'm not decreasing, I'm not increasing. I'm turning around. So there is no change. And then I'm going to start to increase again. So what it tells us, again, if we go back to it here, is if the endpoints on that interval have the same value, or in other words, there was no change in y, then somewhere on that interval you turned around, which means somewhere there is a c value we know whose tangent is equal to 0. In other words, we know there is, or the existence of a horizontal tangent line. So Rolle's theorem helps us prove the existence of a horizontal tangent. So let's go look at a graph for a second on that. So here I have just one example. Here's a partial circle. And what we can see is if I put in my starting points A and B, the output at A and the output at B are both 0. So in other words, the average rate of change there was nothing. So the secant line is just that horizontal red dotted line. So if I see that my change in y was nothing, there's some point C. I'm going to turn the point C on first. Oops. Let's put it down here. There's some point C where the tangent line is exactly equal to 0. So like that point C doesn't have a 0 tangent. It's not there, and that makes sense, right? At first, if I started at A, I was increasing, so my slope was positive. I'm getting farther away from the y value of 0, getting farther and farther away. But if I'm going to make it back to 0 by the input of b equals 1, I have to turn around somewhere. So I'm going to start slowing down, right? So I'm going faster. I'm going to start slowing down, start slowing down, start slowing down, because somewhere right there, I have to turn around. So we found the point right there where our tangent line was horizontal. Again, once I'm horizontal, in order to get back to y equals 0, I have to start going this way. So that's why I have to start creating a negative slope. So you can see that this is where that differentiability comes in. I have to be able to turn around. I mean, it's not a point, it's not a v, it's not a cusp, but I'm slowly turning around, which means somewhere I must get to 0. I'm not jumping values. So we can see that there was the existence of some tangent that was horizontal at some point. Now that could be anything, right? I just chose like a nice little circle there. But again, just as we see over here on these graphs, if I make just a few more, no matter how that happens, you'll find somewhere. So if I look at this, so like here, the x value is 0, and here the x value is 0. So there's probably a horizontal tangent like right there. If I draw another one, there's a lot of different ways this could happen. And same thing with the mean value theorem. It might not tell us how many of those points exist. It just tells us that they do. So if I looked at A to B, the average change in my y value was nothing. So it says somewhere in there, there has to be a horizontal tangent of 0. There could be more than one, but there has to be at least one. And that's Rolle's theorem.